Okay, so if you are using the plant-oriented, plant-related parameter, this does not allow relating the setup of the machine with the treatment result. Okay, if we say in the pin that part with a turning speed of, I don't know, 1,000 RPM, cannot be related to the effect we are considering for, we are obtaining for on a part. And the effect will change with respect of the part we are using. So in other words, what can we say? That if we are using the same setup for treating different parts, the final result is different. And this is even more valid if you are using different kind of plant. We are not able to assess which is the expected result in terms of mechanical performance. So the definition of parameters related to the plant does not make possible at all to put into relation the treatment parameter itself, the technological, let's say, parameter, with the effect we are obtaining. We need the definition of parameter that allow to estimate directly the effect of on the treated part, and to estimate them in a repeatable way, in such a way that we are sure that once the treatment is repeated, we are obtaining the same result, whatever is the plant we are using. Okay, and how can this aim can be achieved? How can we solve the problem? The problem can be solved by considering that which is the main, which is the physical cause, let's say, the physical reason why shot peening is inducing the effect we know, the residual stresses, the roughness, and the surface work hardening. And this is related to what? Finally, we can say that it's related to the velocity, to the impact, but finally to the energy that is associated to the treatment. Whatever is the machine we are using, we have kinetic energy and impact energy for wheel peening machine, and the same kinetic energy associated with air peening machines. Okay, and the cumulative energy that is used for shot peening can be considered as the driving force leading to some result. So the parameters we need to define the way shot peening is done must be related to somehow to the energy we are introducing, let's say, the impact energy we are introducing, the plastic deformation energy we are introducing in the part. This is the final aim. And this can then be related to the technological parameter, but this comes later. Okay, we don't want to define the treatment by using technological, process-oriented parameters, but we want to find parameters that are related to the effect, and finally to the energy. And we can estimate, let's say, we can define the cumulative energy of the shot peening process in two factors, let's say, which is the first is the kinetic energy of the shot flow. This can be due to the turning speed of the wheel. This can be due to the pressure of the air we are using. But we are applying some kinetic energy to the shot flow. And the second time is, if we are talking about the cumulative energy, we should consider also the time of exposure to the shot flow. So the kinetic energy of the shot flow first, and then the total time of treatment. And the concept of the shot peening intensity and shot peening coverage that are used today, universally, let's say, are related to these two factors, to the energy of the shot flow and the total time. So, and now let's see how they are defined, starting from the shot peening intensity. Okay, the intensity of shot peening is considering as we said, the amount of kinetic energy, okay, that is associated that is imprinted to the shot flow. Okay, and the energy is the kinetic energy, and then goes, at least partially, mainly in plastic deformation. Okay, most of the kinetic energy is then used for the plastic deformation, not uniform plastic deformation of the material. Uh, how can be use this concept with respect of a process parameter? How can we use this concept for defining a shot peening intensity? Indeed, we need something easy and fast. We want to apply this definition in an industrial environment, in industrial line, let's say. So we don't need something that needs difficult calculation, long calculation, long analysis, and so on. We need something fast, something that is possible to apply easy and fast. And the concept of intensity that is based on kinetic energy, but and is used today is, as I already said, is the one that was defined by John Allman, initially at General Motor and then universally applied, and is called, of course, the Allman intensity. And the Allman intensity, now we will see how this is defined and how it's related, at least somehow as a synthetic parameter to the energy of the kinetic energy of the shot flow, can be considered a very practical and repeatable way to measure the intensity of the process. That is suitable for industrial application because, indeed, we need just some simple experimental measurement, not complex calculation, some simple experimental method. This is fast, and this is the reason why this definition of intensity was the one that was most successful and is now everywhere used. Let's see a bit more in detail how the Allman intensity works now. What are we considering for the Allman intensity? We are considering to use a thin strip with assigned material. It's a spring steel. Okay, this is fixed. We are not changing the material of the Allman strip. The Allman strip is this one, very thin, and the material is fixed. It's a SAE spring steel, and we can have three different thicknesses of the Allman strip. The thickness is N, A, and C. And N is the thinner one, A is the mid one, and C is the thickest one. And we are using, in generally A is the most widely used, but if we need to define very light parameter, we must use N strip. If we are considering very strong, severe parameter, C strips are the preferred one. Okay, and how we perform the test? Indeed, we consider one of these Allman strips. Okay, we fix it on a block, on an holding fixture, let's say, by means of 3 or 4 bolts, and then we pin it under controlled condition. Here this is a nozzle, so here the figure is referred to air pinning, but nothing is changing if you are using pinning. So the condition, the pressure in this case is fixed, the distance is fixed, and then we pin just one side. The bottom one is not pinned, so we are not turning up and down the strip to pin also the second face. We are pinning just one face, and then at the end of the treatment we are removing the screw, leaving the strip free, and due to the residual stresses by pinning, we will have a plastic deformation that gives a residual arc height here. The strip will not be anymore straight, but will be curved. And the Allman intensity is defined as the height, the value of the residual arc. Okay, this quantity. And this measured by means of a common measuring dial that is for measuring the variation of distance, let's say. This is. And this is the way the concept of the Allman intensity that is in the SAE code J442. That previously was in the military code, now is assumed also in all the other codes. Okay, so this is the basis of the Almen intensity. We are measuring, indeed, we are measuring a length, a residual deformation, let's say, a residual displacement induced by shot peening on a strip, where we are fixing the material and the geometry of the strip itself. So it's quite easy. It's not related. We must not take care of changing the material according to the material we have to pin. Everything is fixed. And by means of what is important is that we maintain the parameter of peening, the peening parameter we use for determining the Almen intensity. We maintain then when we are performing the treatment on the workpiece. Okay. There is some detail about the Almen strip. This is taken from the code itself. This is I wrote the page 5 of the code. Here we see the dimensions are fixed with some tolerance, of course. You see N is the thinner one, A and C. Okay, and indeed, here you can see also what the material is SAE 1070 core roll. This is a spring steel, okay, as I said. And then the treatment is also prescribed, and surface carbon content, and so indeed. In the end, the Almen strip are not manufactured by the company, are bought by a supplier. Okay, there are some specialized companies that sell the Almen strip. Okay, and so we are sure that we are using the right one. They are certified. Of course, we can also decide to machine them, to manufacture them by ourselves. This can be done, of course. We have not, but if we have to draw a quality report, indeed, this is something that can be an object for discussion, okay, for possible customer. Okay. This is the older. This is here in this page of the code. Oh dear. What's happening? Okay. This is the older. Which are the characteristics of the older? Must be rigid. Okay. You see that the thickness is 19. Okay. And to prevent that possible deformation of the older itself are influencing the result. Okay, and must be well aligned. The surfaces must be well done and parallel each other. And in the end, also the screw and the holes must be in the right position to avoid any possible influence of inaccuracy of the machining of the hole of the screw with respect of the result. M5 is the kind of bolt that is used for the holder. Okay. The Almen gauge is indeed this is called the Almen gauge. It's not different from the usual gauges that are used for measuring the displacement and change of distance with respect of a reference point. Indeed, we are using this is design and manufacture for Almen strip. So every geometrical detail is done considering the Almen strip. But finally, from a functional point of view, we are measuring the change of a distance from the condition where the Almen strip is straight, linear, and when it is curved. This is so it's not complex. So now that these instruments are digital, also analogic ones are still used, but anyway, no problem, no different finally in the accuracy of the measurement we can use. It's important that the holder is well done, well designed, and well done in terms of tolerances, because in this case the tolerances can play a role in the final accuracy of the measurement. Okay. Any question?
Sir, any specific reason why we have used this three sheets, namely three strips, NAC, any specific reason for that alphabet, any significance?
Sorry?
Sir, any significance in slide number 33, we are using three strips with varied thickness. So we have named it NAC, any specific significance for it?
Indeed. A is the most widely used. For common peened material and common peening condition, A is the reference. But if we are peening, I don't know, magnesium alloy, for instance, or aluminum alloy, we could need light intensity. And we are not able to get this intensity if we are using A strips, because the residual deformation would be negligible or too low to be clearly detected with the Allman gauge. So we are using a thinner one, N, to make it more evident. And then we will see that in the measurement we can do by using N, A, or C is related. There is a relation between these three measurements. C is used if we must perform peening or on very strong parts, indeed parts that are built by using very resistant hard material. In those cases, indeed, if you are using A, and the peening parameter, the pressure, the velocity is so high, so much that in the end we will not destroy, but strongly damage the strips. And we cannot do that. The measure will not be accurate. So we prefer to use a thicker strip, C, in such a way that thick is not destroyed, and we have anyway a meaningful value of the intensity of the residual arc height.
So in short, we can say that intensity would preferably directly proportional to what is the height or
yes,
the arc.
It is. The arc height is the value of the intensity itself. Okay.
Thank you.
That is not proportional to the parameter, because the deflection of a beam, we know, is a function of the cube of the length, so it's not proportional to the length or to other parameters. Anyway, there is a relation, of course. Okay? Okay. No, any other question? Sorry. Okay, let's proceed now. Let's see now the concept of Allman intensity should be clear, okay? And now let's see which are the parameters that affects the Allman intensity. I'm referring to both air and wheel peening machines. Okay, the shot flow rate, of course, is influencing the Allman intensity. Okay, so the amount of shots that are flowing per second for time unit, let's say, is influencing the Allman intensity. And also, of course, also the shot velocity that is directly related to the kinetic energy. This means that it's related to the higher pressure, if we are talking about air peening, or is proportional to the angular speed, if related to the angular speed, if you are talking about wheel peening machines. The impact angle, of course, because why? If the impact angle is normal, most of the kinetic energy will go in deformation energy. If the angle is far from 90 degrees, we said that a part of the energy will go in friction and will not cause any plastic deformation. Okay, so will not induce relevant residual arc height of the Allman strip. And then the distance from the workpiece that must remain the same when we are pinning the real part. We must not change it, because we know that it's also affecting the final energy, the impact energy of the media. Okay, and it's also true that indeed experimental measurement, let's say, the experimental evidence said that the Allman intensity is not varying so much if the distance is maintained in the range 100 to 200 millimeters. So there is not much different, but anyway should be kept constant if we want to maintain the same condition. If we are talking about the media, of course, the media size and the shot size and the shot hardness are influencing the Elman intensity. If the shot is very hard, it means that the energy will go in plastic deformation of the Elman strip, and not in the deformation of the shot itself. Okay, and the size also, indeed. If the velocity is the same, it means that if the shot has a larger diameter, it means that the energy, the associated deformation energy will be larger. Okay, here we see some graph that should better clarify the influence of some of the parameters with respect of the Elman intensity. Okay, here we have what is represented in this graph. In the horizontal axis abscissa, we have air pressure here, and in the ordinate, we have the Elman A intensity. So we are talking about Elman strip type A. And we have different shot size with different curve. Each curve represents a shot size expressed in millimeter. And we see that these curves are, in terms of relation between the air pressure and the Elman A intensity, is almost linear. These are approximated, but they are valid indeed, are reliable. Okay. And in this case, you see the Elman intensity is expressed in what does it mean, A millimeter? We are talking about A, strip A, and the unit is of the residual deformation, the residual display, the residual arc height is millimeter. If AMM is not used, but just A is used, it means that the result is expressed in inches, okay, in the American unit. That was the inches was the original unit used for the Elman intensity. Today, millimeter is widely used, so it's better to specify what are we referring to. Okay, here what can we see here? Here we see two different curves that refer to different. Okay, here I'm referring here to air peening, but similar result can be reached by considering different turning speed if we consider a wheel peening machine. And here we have the distance expressed in inches this time on the abscissa, and the Elman A in the ordinate A. Okay, here. And we see that in this case, if we consider the arc height of the Elman strip A expressed in inch and the distance, and the relation is not curved. We have a maximum at some distance, and then if it's decreasing, here is a slight increase according to this curve, and here is finally drops the Elman intensity drops down and is decreased, and then it's unmeaningful to go over. Okay. Now the correspondence between A, C, and N strips. Okay. What is represented in this graph? Here we have two curves, N and C, and here we have A, Elman A strip values. And we have that the relation between A and C is about to be this. A is 3.5 times larger than C. And this is expectable. Indeed, C is thicker, so the residual, with the same condition, the residual arc height will be smaller, lower than A, and the quantity, the coefficient is around 3.5. While if we consider N, this is around 3 times larger than A. And for the same concept, the same concept can be applied to this relation. Okay, so C, A, and N are not independent, they can be related. What is indeed, and when are we using this relation? To have, if we are used to consider A strip as reference, but due to the particular case we must choose C on N, this give us an idea of how severe or how light is the peening we are doing. Okay, this is just, we have since most of the people is used to deal just with A, have an N value equal to 12 or whatever it is, could be not so meaningful. It's better to make the conversion to A in such a way that we have a clearer idea of the severity of the treatment we are doing. Okay. And now some note about how the Almen intensity is measured. Indeed, which is the process before we are measuring the final residual arc height. Okay, and this is what we are doing. One strip is not enough. First, we must use more than one strip. We start from the first strip. We assume a treatment time that can be this, according to the experience. We measure the residual arc height here, and then we pin a second one. Okay, by doubling the time, and again we repeat the measurement of the arc height, and it will be this. Okay, and we repeat, we goes on, we proceed, and we repeat this operation more, 2, 3, 4 times, let's say. And every time we measure the residual arc height of the strip we have used. And when we see that the difference, the increment of the arc height of one strip with respect of the previous one or the other one is less than 10%, it means that, okay, here, of the previous one here is less than 10%, it means that we have saturated the strip. It means that if we are prolonging again the treatment, nothing will change. We have saturated the strip. Okay, so we start from this point. We note, we write this, or we put in the computer the value. We double the time, another value. We compare the two values of the arc height, is more than 10%. We must pin another one. We pin a third one, okay, and then another one, and so on, till we compare the last measurement with the previous one, and if the difference is less than 10%, it means that that's all, that's enough. It means that we have saturated the ability of plastic deformation of the strip, and we can stop the procedure. And the final, okay, the final value of the Almen intensity will be that one. Okay? When the increment is less than 10%. Okay? Or in other words, when we find that by doubling the time here, this is more quantitative evaluation, we double the time with respect of this, and the increment is less than 10%, this means that we have saturated the ability of the strip for plastic deformation. Today, a Canadian company is developing a digital strip. That is to say, by using algorithm and software and so on, we are able to use maybe just one strip, and then we can elaborate digitally, with the digital twin, let's say, the final expected arc height. And this is an advancement, of course, make the procedure much faster. Okay, and this is done. Okay. By the final recap, we must use different Almen strips. Okay, we consider the arc height of each of them. When we find that by doubling the time, an increment of less than 10% can be obtained in terms of arc height, it means that we are in the saturated condition. No other further increment of the arc height is possible. And this is the final value of the Allman intensity we have got. We should consider in our specification of the treatment. Allman intensity with this air peening parameter or with the wheel peening parameter is this. Okay? Any question? Is clear the concept? Yeah. Just a moment.
How to correlate this height, like Allman strip height with this energy value? Is there any correlations you have to make, or like?
Have to correlate the Allman arc height with?
This energy input, like energy of the short peen displacement.
Indeed.
Yeah.
The question is a good question. Indeed, the Allman intensity is a synthetic index because indeed the kinetic energy, indeed the impact energy go in plastic deformation.
Yes.
But it's true that this way to define the intensity is not complete from a physical point of view, let's say.
Okay.
What does it mean? That we can obtain, if we refer to microscopical effect, let's say, we can use different Allman intensity to get the same residual stress field. So this is a macroscopical parameter that is related to the energy, of course, because it's increasing by increasing the energy of the shot flow, but it's not complete, of course. But anyway, it's good because it's fast and cheap in the end.
Yes.
This is the reason why. But if you are wondering how this is related to the energy, this is just a synthetic parameter, nothing more. Okay.
Finally, calibration may be needed, or like that. Calibration we will do. Calibration with the existing non-energy we will pass, and we will check the height. Like that way, we are correlating with the height and energy input. Like
the final relationship can be found, of course. Indeed, so far as to my best knowledge, no one did that. There is not any analytical relationship between the energy and the effect of the peening parameter on the Allman intensity from an energetic point of view. Okay?
Okay, sure.
Okay. Let's see some picture now. Okay, how indeed in a production line, how the intensity is measured. It's important to put the Allman strip and the Allman holder in the right point where we want to pin the component. Here you see a blade with this Allman strip and Allman holder that is fixed to the surface. Here you see, here is another Allman holder. Indeed, in all the points where we are performing shot peening, we are putting some holder, Allman holder and Allman strip. And here, indeed, it's not clearly visible, but there is the nozzle to measure, to pin those parts. And then we pin the Allman strip in the same condition, in the same direction, same condition, same distance of the real part. And then we perform the process, the measuring process we have commented just now. Okay, and then finally, when the Allman intensity is measured, and it corresponds to the one that we have considered during the design stage, we can pin the part according to those parameters, okay, to respect the design Allman intensity. Okay, indeed, we are performing short peening, of course, after having designed the treatment. And design the treatment means that we have already chosen the Allman intensity and the coverage, that is the other parameter we will see in a while. Okay, and here the same. Here there are some other components, and here you can recognize the Allman strip holder and the Allman strip that are fixed where shot peening will be performed. And in this way we are able to to measure, which is the Allman intensity induced by peening with certain parameter according to this position. And finally, we are able to set up the plant in such a way that we respect the parameter, the intensity we have chosen, we have prescribed during the design of the treatment. Okay. Of course, shot peening is a process and must be correctly designed. Otherwise, the result will be not aligned with the expectation, of course. I remember that I was younger, there was a professor that I was continuously discussing with him about it because he said that shot peening is not good for fatigue because in his experience he had to deal with a case where shot peening did not prevent a fatigue failure. So this is what he was convinced that it was not good. But the problem was in that particular case, shot peening was not well done or not well designed. This was the problem. But anyway, no reason. Every time he was convinced of this issue, of this point. Okay, anyway, let's go on. And let's talk about the coverage now. Okay. Coverage is the other parameter. We said, I go back a bit, and then, we said that if we are referring to something that is related somehow with the cumulative energy of the treatment, we have two factors, the kinetic energy of the shot flow, and this is the Allman intensity. This is directly related to the kinetic energy. And the second is the total time of the treatment. Okay, and coverage is referred to the total time. Okay, and indeed, what does it mean, the surface coverage due to shot peening? It means that, indeed, we reach 100% coverage once the complete surface we want to peen is peened. Okay? And the coverage is considered as the time needed for peening the 100% of the surface. Okay, so, and the measurement, we will see that I can anticipate that the measurement of the coverage is performed by means of, in the simplest way, by means of visual or optical microscopical observation. Okay, and we are talking about cumulative energy, that we are referred to the time we need. It is not the kinetic energy of the shot, but the number of repetition of impact. Okay? And 100% coverage means that the complete surface has been interested by at least one shot indentation. By observing the peened surface, we cannot observe any untreated part. Here, indeed, maybe here is not very clear, but probably in the paper is more. Here there are two pictures taken with 50% coverage. This means that around one half of the surface has been peened and the otherwise is still unpeened, and then 100% coverage. And by looking at the figure, the difference is clear. And what does it mean, 200% coverage? Indeed, I said that coverage is related to the time. If we know the time we need for getting 100% coverage, 200% means that we are repeating the treatment using doubling the time. This is what we are doing. We are considering a time that is twice the one that is needed for getting the 100% coverage. Okay, it's clear the concept? Yeah, just a moment, Kate.
So here 200% coverage means this time has doubled.
Yeah.
So 50% means 50% surface has covered or time has decreased by 50%.
200% means that indeed we must fix the time needed for 100%. We
Okay.
define the trajectory, the path, and then we know that the
Yes,
complete
yes.
surface has been pinned.
Pinned, yes.
200 means that we are repeating this treatment another time.
Oh, okay, sure.
Okay, and we can go even
Okay.
larger, 300, 400, 500
Yes, yes, okay,
coverage
sure, sure.
degrees we can do.
Oh, okay, okay.
In
Understood.
industrial application, 100, no more than 200 is usual.
Oh, okay.
Indeed, let me say that also 98 is considered, we will see in a slide later, 98% is considered acceptable. That is to say that small discrepancies with respect of full coverage can be accepted, can be tolerated. Okay.
Okay. So 50% means only 50% area has been covered.
Yeah.
That's all. Okay. 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 Sure. Sure. Okay. Thank you.
Okay.
Thank you. It's okay.
Sorry?
Possibility that it may reach the saturation also.
By increasing the coverage.
By increasing the coverage.
Indeed, it's a possibility that if we increase too much the coverage without the right assessment and without the right intensity, we are performing overpeening.
Oh,
This means that we are damaging the surface. This is a possibility.
Yeah.
Okay, and indeed the difference between severe shot peening that is still positive, where we are obtaining grain refinement, and overpeening that is negative, because we are damaging the surface, is borderline, let's say. It can be confusing. Okay, this is true.
Sir, in slide number 37, sir. 37.
37.
Yes, sir. That distance, in the slide number 36, it is stated that distance between the workpiece and...
This one?
36, sir. That in the 36 page number,
36,
slide number,
sorry.
it is stated that distance from the workpiece,
Yes.
AI remains almost constant. But here in the 37, if you see in the range of 100, that is 100 is actually 4 inch. That
Yes.
is not in, it is not constant. Is it?
No, it's not
am I
constant,
reading right or wrong?
But
Or
here, if we consider the plafond here, it's almost flat. So it's not constant, but the variation is not very steep, let's say. At least in this range of variation of the distance. Then is greatly changing, of course. Okay.
thank you, sir.
Okay, we can proceed. Okay, let's now proceed. And indeed, as I said, the coverage is the ratio is the percentage of the pin area with respect of the total area, the full workpiece area, let's say. And so the coverage can be defined as the sum of the area of the single indentation over the total area, full workpiece area, multiplied by 100, of course. And the pinning time is related to the single indentation and the coverage in the end. Okay. What is S? The pinning time is a safety factor that considers the possibility to overpinning and also to underpinning. That is to say that the coverage is too low. Okay, as I said, 90% is considered as acceptable. Okay, and what can we further comment? Okay, coverage is the ratio of the intended surface area with respect to total surface, and this is done, this is understood. Coverage must be measured on the component itself. Okay, we don't need any other tool, and we don't need another part, something like an almond strip, an external component. We measure the cover directly on the pinned part. This is what we are doing. We are considering the pinned part. We go there with some tool that we will see, and we measure which is the real coverage. And then this can be considered as satisfactory, or if it's not the case, we must perform again pinning till the expected coverage condition are reached. Okay, which are the factors that are influencing the coverage? Okay, and this is related to the way the kinetic energy is transferred in plastic deformation for the workpiece. Sorry for the typos of the shot flow. The shot peening system type, okay? The shot peening plant is influencing the coverage and the way the peening indentation are distributed. So this means or the nozzle that is directing the shot flow, or the geometry of the fan blower, that if this is for wheel peening machine. The speed of the shot, no need to add that if the speed is larger, the indentation will be also larger, and so from a theoretical point of view, the number of impact we need for getting the full coverage will be lower, the number of indentation. And the impact angle is also affecting the area, not only the area, but the shape of the impact area and the impact area itself. And so also this impact angle is another factor affecting the coverage. Okay, and now indeed, let's see now this graph. This must not be confused with the graph, the similar, qualitatively similar graph I show for the Allman intensity. Also, this graph has an asymptotic trend, okay? But indeed, the meaning is quite different. We are talking here about coverage. And here you can recognize the difference, the visual difference between what? Between a peening that is covering 10% of the surface, 30%, and so on, till 98, let's say 100% of the surface. That is the last point. Okay? And indeed, we can, first of all, the relation between the coverage, the time, let's say, we need for coverage, and the coverage itself, and the area that is interested by the shot peening indentation is not linear, first. We cannot refer to a linear relationship, but indeed there is a function, an exponential function as a function of time that make possible to estimate the coverage. And this is the Avrami function that is here reported. It is 1 minus A1 to T. T is the peening time. A1 is the coverage as a percentage after time unit. So after a unit of time, 1 second or whatever it is, this is the function we are using. Okay? And do not forget this fact that imagine we are assessing the coverage and we say that if this is the time needed for a coverage equal to around 50%. Okay? If we are doubling the peening time, this is more or less the point, we are getting not 100% or something similar. We are quite far from 100%. We are 75% coverage. Okay? And this is not good. Okay? So we could rely on a linear relationship, but we need to take care of the nature of the process. So if we need a coverage, if we want to calculate full coverage, 98%, 100%, let's say, we must go not with doubling the time, but the time is much larger. So if 50% is around 20, 30 peening time unit, we are here around 120, much more. Okay? How can we check the coverage? The other aspect is this. Now, the concept should be clear now. The trend, the function we can use to estimate the time needed for getting the full coverage is also fine. If we want to go beyond 100%, it's enough to repeat the teeth in the same way for more time, for 2-3 times, or what is this for time, and then that's done. The other aspect is how to check the coverage, and this is the way we can go. The simplest way is the visual inspection, that is the standard inspection. So we take the part, we look around, and finally if we are expert, we are not new and we are used to consider shot peened part, we can with a bit of attention, we can assess if something wrong is in some part of the peened part. Okay, this is, okay. It's clear indeed. If the coverage is quite low, it's clear to understand that it's not enough. Okay, if we are using a microscope, indeed, this is a final estimation if the coverage is increased. Because when coverage is 90% or 100%, with a visual estimation without some lenses of some optical microscope, it's not so easy to detect possible weak point or where shot peening has not been done. Okay, so we don't need a large magnification factor. 50 times is enough, but anyway, it's better to use that. Okay, so this is optical. Other ways to detect the coverage. Indeed, they are not complicated. We can use visual inspection with a digital microscope that make easier the observation and the quantification of what is missed. We can use blue ink that is applied before shot peening and then should be removed after shot peening. If black ink remain in some part, it means that close to those parts, shot peening was not done correctly. And also we can use some replicas, but indeed is more theoretical than a practical way to go, because this is long and easy and is expensive. We need some acetate plastic replicas. We put it on the peened surface, and then we put on the microscope, let's say, and we see if everything is well done. It is not common to perform the check of the coverage this way. It can be used in parts that are not easily accessible, such as the internal surface of the hole and so on. We can use also fluorescent tracer. Okay. How does it work? Workpieces are coated with a fluorescent tracer before the treatment. The coated area radiates a light color, light blue, when exposed to ultraviolet light. And for coverage greater than 100%, the radiation of the coating is no longer visible. The tracer has been removed. Okay, and so this is a more refined way to proceed, and this is useful to adjust the nozzle in air peening and to ensure the daily reproducibility. This is combined many times with visual standard method. Here you see the difference of the observation of a part that must be peened before peening and what we can observe under the exposure to ultraviolet light after shot peening. And you can imagine that if some part is not covered, indeed the reflection, the light, the color will be quite different, will be quite lighter. And so can be, this way the possible weak parts can be easily detected. Some critical point about the check of the coverage. If we have hard surfaces, indeed, the contribution of shot peening in changing the surface roughness will be not so evident. The indentation, if the surface is hard, the indentation will be also small, and the final finishing will be not very, very different with respect of the initial one. So a problem could be on our surface that is not so easy, not so immediate to detect possible not peened part of the surface. Okay, indeed, if we are using visual inspection, but also microscopical inspection, indeed the sensitivity, the expertise of the operator plays a role. Okay, indeed, if we are on a borderline, let's say, and to pass or not pass some peening condition, the sensitivity and the expertise of the operator could make the difference. So, and the check of the coverage, the ways we have seen, is subjected to this subjective assessment, let's say. So could be a problem, and it's better if there is some possible issues about acceptance or not, it's better to request the opinion of more than 1-2 operators with diverging opinions. Okay, sharp edges are difficult to observe. Also, this could be a problem. If we have complex geometry, we have no line of sight to correctly inspect the coverage. Okay, and this is a particular case, give false coverage, correct coverage as impact are not related to correct intensity. Identification of critical zone needs special check. And finally, let's see that, let's remind something that about coverage and intensity. Because sometimes these two concepts are confused, but they are not, they are independent factors, okay, and are independently checked. No way to consider coverage as something related to intensity or not. This is two different things. Also, the time that we use for assessing the saturation condition for intensity is quite different with respect of the time we need for assessing the coverage. And do not forget the intensity is checked by using a strip, while the coverage is checked by using the workpiece. Okay, so which are some comments? Intensity is a nominal measure of the rate of energy transference available for the process. It does not vary with the exposure time. Whatever is the exposure time, and the coverage is 100%, 200%, or more, the intensity remains the same once saturation is reached. Okay, saturation of the Allman strip, I mean. Okay, the coverage is a nominal measure of the work done to the part processed. It's a function of the exposure time. This is done, this is understood now. The changing of the coverage on a part does not change the intensity of the process. And this is what I said, indeed. If we use coverage that are more than 100%, this does not mean that the intensity also is changing. It remains the same. Changing the process parameter, of course, can influence both the coverage rate and the intensity. Okay, if you are changing the process parameter in terms of technological process parameter, this could have a reflection, an effect on both the coverage and the intensity. Okay. Some other comment to highlight the difference of these two concepts. The determination and inspection of intensity is done by using the Allman strip. The coverage is not done in such a way like this, but is measured directly on the workpiece. The Allman intensity gives information about the energy of the treatment, the coverage about the total time, or we can say also the accumulated energy, the total energy that is induced in plastic deformation along the complete duration of the treatment. And indeed, MFN is a magazine that I cooperate with, and they agreed me to use some of the figures that I use in this presentation. So this is acknowledged. Okay. Okay, this is for, and it's time for possible question now.
Sir, assuming that we are going for wheel peening, okay, and preferably this is the area where the shot peening has to be carried out. So is there not a possibility that some region of this particular area might have gone for 100% coverage, and the other region of the same surface might have gone for 50%, or some area might have gone for 200% coverage. Is that not quite possible?
It's possible, but indeed, what is always true is not all the complete surface is interested by the same number of indentation. This can be divergent. If you have a part that is 200% and the other one is less than 100%, it means that the way you have designed the treatment, I'm thinking to air peening and the trajectory of the nozzle, was not correctly defined.
So
okay.
if we are going for air peening, that concept of nozzle comes into play, where we can actually control the trajectory.
We should correctly design the trajectory of the
But if
nozzle.
we are going for the wheel peening, where we don't have much control over the trajectory, double indentation might be possible.
Indeed. This is a preliminary assessment. We have not a strict control if we are using wheel peening machine, but we have experience, so we know the arrangement. We can imagine the arrangement. But anyway, when we are considering a new application, some preliminary test is needed. Of course, yes.
Okay, thank you.
No other question? Well, okay, we can go. So let me, indeed, we have no time to finish the next presentation, but I will start and then we will complete tomorrow morning. This is about, now we talk about if there is any other question, if there isn't any other question. We talk about the process, we define the parameters, the general parameter define the process, the media, the intensity, the coverage. The next step is to talk about the effect and how the effects are related to the parameter. This is the key knowledge that makes possible to design a shot peening treatment. As I said, shot peening is a process, is a technological process, such as all the other technological process. We need to design it, and if we want, it is well done. Otherwise, the result we expect are not going to be satisfied, to be obtained. Okay, and so let's see which are the effects and how this mechanical behavior and the effects are related to the treatment parameter. So this is the outline of this presentation. After the brief introduction, we will see, we already know, I have already mentioned which are the three main effects. Residual stresses, surface microstructural modification, microstructural change, both in terms of hardening or in terms of also in grain refinement, and finally the effect on surface finishing, surface roughness. Okay, and now indeed, we have already seen this figure, and I'm recalling it. Why? Because it makes evident to recall these three effects. We have an incident ball, an incidence media, and a rebounding, and the same that is rebounding, and after the impact we can notice grain distortion with an increase of and a gradient hardness, a change in the surface roughness, morphology, let's say, and then due to the not uniform plastic deformation of the surface layer of material, we have the introduction, the generation of residual stresses, compresses close to the surface. Okay, indeed, I'm not going to comment again this figure because we have already seen that. I will comment the second one that is similar, conceptually similar, but is more strictly related on shot peening. It's focused on the contact of shot peening. Indeed, if we consider the contact of balls, let's say with a flat surface, not only flat, but we can consider it as flat, we are in the so-called non-conformal contact condition, also called, at least in the linear elastic field as regards the behavior of material, the constitutive equation of material, we have in the linear elastic field. The contact problem is not conformal problem, contact problem is not linear, but not for the material, for the geometry itself. That is to say that the pressure is not varying proportionally to the applied load, because the contact area is also varying not proportionally. Okay, what is and so in this condition, if we have a sphere, let's say, with a flat surface or with a regular surface, we are in the so-called Earth contact condition. That is to say that that the relations between the applied load and the pressure distribution and the stress distribution, starting from the surface going deeper, are given by the Earth theory. And this is what is shown here. We have an elliptical pressure distribution that is the one given by the Earth theory, maximum in the mid of the contact area and then decreasing with an elliptical shape. And in terms of stress distribution, these are the stress components that are due going from the trend in depth, going from the surface here to the z-axis is the depth, going far from the surface. We have the sigma z and sigma y, and the tau stress, the tau shear stress, that is null of the surface and then maximum under the surface. Okay, and then we have the other effect is this. This is referred to the single indentation. Here we imagine to apply the full, it's an idealization of course, the full shot flow at the same time on the complete surface. And this can be approximated somehow, ideally, let's say, as a stretching of a surface layer in terms of surface hammering, much more general. And finally, the stress distribution, the residual stress distribution induced by shot peening is superposition is due to these two effects. The Earth contact has the stretching effect due to the multiple indentation of the shot flow. And we have, in terms of Earth, we have this residual stress distribution with a compressive residual stress on the surface, and the peak under the surface is in depth, at the depth that is related to the applied load, let's say. If we refer to the effect of stretching, the trend is this, with a maximum in the free surface and then rapidly decreasing and then becoming positive at the cell train depth. And the same happens for the Earth distribution. The final residual stress distribution due to shot peening is the sum, let's say, is the superposition of these two effects. For some parameter, the Earth effect will be dominant with a peak under the surface. For other parameter, the peak can be also on the surface. Let me say that if we consider steels, many times the peak is under the surface. Talking about aluminum alloys, it's not rare to have peening parameter that induce a peak at the free surface. But anyway, this is a consequence of the applied parameters. Okay, and this is, again, another way to see a similar concept. What can we see here? Indeed, here we can see an indentation. Let's see, a surface that had been peened just in a single point. This is a peen surface. We have a depth at here where we can, that is the depth that is influenced by the stretching, let's say. And what's happened? That, indeed, due to the plastic deformation, the surface layer of material, the material that is in the D, within the D depth, is stretched plastically. So it's not going to have the same, when the load is over and the peening is finished, it's not going to return in the original position. So each point in that region in the layer of material under the surface and on the surface is not going to move back to the original position. This is plastic deformation. What's happened? That the layer under D, the deeper layer, try to go back to the initial position because they are not plastically deformed. They are elastically deformed. But they cannot because the upper layer prevents this going back to the original position. Okay, and so what's happened? That they press over the surface layer of material, causing the generation of compressive residual stresses. Okay, and this is what happened with shot peening, with a final trend that is this one. Okay, with a peak that generally is under the surface, and then the residual stress that after a while, after some depth, becomes positive, tensile, because we know they are residual stresses, they are set stresses, they are self-balanced. Okay? Here a bit more quantitative trend of residual stress, typical one, let's say. Okay? Here you can see the value expressed in megapascal. We are talking about a maximum that is around 700 megapascal. Okay, on the surface we have around 400 megapascal. Well, so we can say that the material is not written here, but anyway we can say we are talking about a steel. Okay, a low alloy steel probably. Okay, and what I would like to remark is this, that the typical point that define shot peening residual stress trend. To define it, we need to know the surface stress, this one, for around 400 megapascal compression, the maximum compressive stress, that in this case is around 700. Here is not remarked, but also the depth at which the maximum compressive stress should be also noticed, should be also considered, and finally the depth of compressive layer here. Okay, the quantitative, and if we want to estimate the effectiveness of shot peening, if you want to have an idea, a quantitative idea of the parameter you want to apply, we should apply to get some improvement, we should know this value. We should know how the residual stresses are changing from the surface to in depth. Okay? This is important to know. And this is the way these parameters are changing, okay, by changing with the different parameter of the treatment. So what can we notice? That this is a qualitative trend where the surface stress, the maximum residuals, the maximum compressive stress, and the point where the stress change sign are evident. And we can notice that the maximum compressive stress is a function of the shot velocity. Okay, and so we can say that it's directly related to the Allman intensity. Okay. The Rm is the UTS, or we can call it also UTS of the shot and the component are also influencing the maximum compressive residual stress. Okay, and the diameter of the shot and the SKS is the area of the surface. No, the loading stress during peening is here. I was forgetting that. Okay. What is loading stress during peening? Indeed, loading stress during peening is important if we are applying stress shot peening. That is, so if we are applying shot peening with the concomitant contemporary application of an external load. Otherwise, the SKS is null, of course, and is not a usual way to perform shot peening. And the depth at which the maximum compressive stress is also influenced by what? By the velocity of the shot. An increased velocity increases the depth where the maximum residual stress, compressive residual stress is, the diameter of the shot, and again the SKS. if the component increases the UTS, RM, in this case, the maximum residual stress depth is going to decrease. Okay, someone could be remained a bit confused by noticing that if you are increasing the strength of the component, the maximum residual stress is going to increase also, but this should be considered not with the same velocity. Okay, it means that if you want to get the maximum compressive residual stress for a more resistant material, we need to increase the velocity. And finally, if this is the right one, we can induce a residual stress that is more effective than for not so well resistant materials. Okay. Again, here in this similar concept, and maybe a bit more complete listed. This is here is not only the maximum compressive stress, but also the surface residual stress. And what can we notice without? We have already commented most of the parameters. This is referred to air peening because I see pressure, and the time is also a factor that is influencing somehow the trend. And the hardness of the shot and of the material is related to UTS. Okay, and indeed, I repeat, why this is important? Because if we want to design correctly design the shot peening treatment, we need to know how the parameters are related to, especially to the residual stress field. Because finally, we will see tomorrow that the residual stress field can be used for using some fatigue strength criteria and assessing the effect of residual stress and finally of shot peening on the improvement of fatigue behavior. So we can use the residual stress estimation of measurement for fatigue design in the end. So shot peening is not only a palliative for improving fatigue, but is also a design method for improving fatigue immediately during the design stage of a component. I don't know if I have other time or if I... Sorry? We can extend up to 1 p.m. Okay. Okay, let's go. Okay. Let's see some other influence of the hardness of the shot here. We see here two different, indeed, all the other parameters are the same. What is changing here is the hardness of the shot. The one could be cast iron, the other one cut wire, okay? And we see that there is a severe influence of the hardness of the shot. That is to say that if you have to deal with hard materials, hard workpiece material, it means that we should use the harder one. Otherwise, we are losing part of the kinetic energy in deforming the shot themselves and not the workpiece. Okay. This is referred to the influence of the speed of the shot. Okay. Here we see the residual stress as a function of the depth, and we see that we have the not peened situation with a residual stress that is slightly tensile and then go to zero rapidly. And then we can see that the residual stress then is strongly influenced by the velocity of the speed. So by the wheel turning rate, less turning velocity, or by the pressure if we refer to air peening. Here we have two possible values. One is 23 meters per second, and we can see that the depth of the residual stress trend induced by shot peening is limited, let's say. The final maximum residual stress is not strongly different with respect of the one performed with the higher velocity, but the depth of the material subjected to compressive residual stress is quite shorter, something less than 0.2 millimeter. While if you are considering larger speed, larger velocity of the shot, in this case 81 meter per second, indeed the most remarkable change is the increased depth of the treated layer of material. Okay. This is about the influence of the static mechanical strength of the peened material. Okay, also in this case, they are quantitative and anyway, but just to give you an idea anyway. Indeed, what can we see here? We are dealing here with very resistant materials. Okay, but anyway, we can see that if we increase the strength of the treated peened material, first, and this is not seen in this graph, we need to apply more severe parameters to induce deformation, induce plastic deformation. But secondly, we can get much more larger compressive residuals in the surface and under the surface. Okay? And how the maximum, indeed, what can we anticipate now, looking at this graph? Indeed, we can anticipate that the maximum residual stress we can get is related to the mechanical property of the material. In particular, it's related to the yield stress. Okay. Once, indeed, we have a maximum that is related to yield stress, if we are increasing the energy or the coverage, finally, the maximum remains the same, but what is changing is the depth where the maximum is. That is to say, by increasing the energy, finally, we are not changing anymore the maximum compressive stress, but we are changing the depth that is subjected to compressive residual stresses. Okay. Okay, and then some other point about the material and this effect. Indeed, do not forget that the final effect can be different if we consider different materials. Okay, yeah, but from a quantitative point of view, but this is what we can say. Increasing the shot diameter and the intensity, we are going deeper. We are using, and the same here, increase shot diameter and intensity, the residual stress is getting deeper and deeper, and so on. Here is for carburized and nitrogen, so surface hardened steel. And indeed, what is happening is that due to the higher strength, static strength of the material, we will be able to get more evident residual stresses, more, okay, related to the UTS of the material. At the same time, the depth of the compressed area will be smaller than the other material that, due to the increased mechanical strength. Okay. Some remarks about coverage. Coverage is not considerable effect in the residual stress state. Okay, if we are using very large coverage, I mean 800, 1000 coverage value, the surface compressive residual stress can tend to decrease. And this means that if we are in this condition, it means that we are going to reach the overpinning condition. We are going to relax what's happening in the surface due to the fact that some surface damage is going to happen. And this is also even more mitigated in the case of severe shot peening, where the surface residual stresses are going to decrease, but at the same time, remaining valid for improving the mechanical strength. Okay? Any question? Yeah.
So in fatigue point of view, which is more preferable? Like, should we get a larger compressive residual stress, or should the depth of the compressive residual should be more?
Indeed, indeed, we should consider that under fatigue loading, residual stresses tend to relax, are partially lost. During the first 10,000 cycle, we lost partially the residual stresses. So what is important is that we have a suitable depth where we have compression. So even if they are going to relax, this is a bit reduced, but the effect of compressive stress remain valid. Okay, this is valid especially for high-strength material, for steel and high-strength material. For aluminum alloys, the usual way to apply soft peening is to try to induce the maximum stress close to the surface. So what is important, this is for the practical application who is performing shot peening with this alloy, say that this is due to the damage mechanism of aluminum, this is more effective. Anyway, I would say that it's better to try to induce a suitable deep residual stress field. If it's too superficial, we risk to lose the benefit in a few cycles. And if you are considering a very thin compressed layer, we are going more in the field of sandblasting, that is, whose effect is not important for fatigue. It's just changing the surface finishing, but not deep residual stresses that are going to be relaxed soon during the service condition. We are not satisfied.
Like, so if all the conditions are same, and due to some thermal treatment, or say annealed steel is there and normal steel is there, and we are doing this same processing parameters, peening parameters are same, so then we will be getting two different depth of residual stress.
If the mechanical properties of the materials are different, if you use the same parameters, same shot, same intensity, the result will be different, of course, yes.
And so this will be affecting the fatigue life too?
Yes, of course.
Okay.
And now we have talked about residual stresses, but we have also other factors, microstructural modification and surface finishing, that are all of them are affecting the fatigue behavior. So if you are using in other words, if you are using too severe parameter for a soft material, we are inducing residual stress, but at the same time we are strongly modifying the surface roughness, probably losing at least partially, if not totally, the benefit coming from the residual stresses. So everything must be correctly tuned and balanced, let's say, each effect.
Thank you.
Sir, regarding the measurement of the residual stresses, so what kind of method that you have followed?
For measurement?
Measurement.
Indeed, there are many methods. I'm using the XR diffraction, okay, the diffractometer. Indeed, today the diffractometer are always seen as just lab facility, indeed, and used for small part. Today there are many equipment where the part is fixed and is the tube and the detector that is moving with respect of the part. And this is the case for residual stresses on mechanical parts. And the method indeed for metal is accurate, especially for shot peened part, due to the microstructural modification. Generally the diffraction peak are well done, are clear. And so the measurements are generally accurate. It means that if we have minus 400 plus minus 15, 20 megapascal. and it's quite good for this kind of measurement. And if we refer just to the surface, it's also not destructive. We don't need to cut, to remove material, to apply any drilling for residual stress measurement in this case. But it's true that we could use also other methods. The most, apart XR diffraction, the other method that is used is the oil drilling method.
This meeting is being recorded.
What does it mean? That we are using 3 strain gauges, strain gauge Rosetta with three strain gauges in defined 120 degree each with respect of the other, around the point where we must measure the residual stresses. We drill a hole with a not very invasive drilling device, and then we measure the relaxed deformity, the relaxed strain at these 3 strain gauges. And finally, by means of formulas, we are able to relate this relaxed strain to the residual stresses at the measurement point. It's good, it's faster than, if you want to go in depth, this is faster. Even at the surface, it's destructive. We need to drill a hole to relax the strain.
But sir, in the case of XRD, we can get only on the surfaces, right? So how you are getting into the...
With XR,
yeah,
we need to remove material, and we can do that by electropolishing or electrochemical removal of material. We must not use mechanical tool, otherwise we are changing the curve, we are changing the gain. That is to say, we are adding residual stresses and we are changing what we are measuring. We need to use electrochemical devices. And it's true that when you are going in depth, indeed, anyway, whatever is the method, something is changed, because by removing the material, we are somehow changing the original state. But there are formulas that you can apply to calculate the original residual stresses. In most of the application, the difference between the original state and the one that we measure when we remove the material is around 10-15%, no more than 15%.
Sir, on your slide 10, sir, in the case of not peened samples, the residual stresses is getting reduces into 0 after somewhere around a 0.4 depth.
This is some finishing process that gives, could be turning with some parameter that gives slight.
It is becoming 0, right? Approximately to 0. But in the case of the velocity equal to 23 meter per second, so the residual stress is crossing beyond that. Why it is so?
Sorry.
It is transforming from compressive to tensile after a depth, like from...
What's happened here?
Yeah, yes. Why that?
Indeed, in this case, we have this, here it is tensile, it goes this way, and finally it will be reduced to 0. It depends on the depth, yes. Okay. And here is deeper, but the trend will be the same, something like this, and then it's moving to 0. The final result must give that the overall tensile and compressive stress must be 0, must be balanced. Okay? Any other question? No. Where is Anna? You.
If the velocity is much less than this one, but say if you are going...
It's very soft here, yes. 23.
So there is a possibility that there is some elastic deformation, and it will recover after, like once the load is removed, it might recover, right?
It might?
The elastic recovery might happen inside the material. Yes. So in that case, there won't be any microstructural change? Or
no, if we have, indeed, if you obtain residual stresses, some plastic deformation
Yes,
is there.
yes.
But if it's very slight, indeed, and the elastic deformation is not negligible, finally the microstructural change will be quite limited, and limited to a very thin layer of material, so, and not influent on fatigue strain, let's say.
Yeah. So will it affect the residual stress in such cases? If it is not plastically deforming the microstructure?
If you want residual stress, we must have
Deformation.
deformation, plastic deformation, some plastic deformation, otherwise we cannot have. Okay.
Okay, thank you.
Okay. It's okay. Okay, let's go. It's the same. Okay, if you want to stop, I can stop, and keep on going tomorrow, or I can proceed with 10 minutes. No, I think we have time for doing it also tomorrow. No problem. I think. Okay. 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 And now finally, let's consider fatigue. Okay, fatigue and the influence of residual stresses on fatigue. And this is indeed, I think that these graphs are quite clear to understand the role of residual stresses. What is shown here? The SN curve here. So we have the amplitude we know, and the life cycles. And here we have residual stresses with respect of the depth. And we have different SN curve, and each SN curve corresponds to a residual stress distribution in this part. This can be a shaft, could be a shaft with longitudinal residual stresses. Okay, and what can we see? We have, okay, preset minus 0.3% and so on. What does it mean? That here we have one curve refers to the preset only. What is preset? We have, or pre-stressing. This is the treatment that we have considered yesterday. Okay, that is to say we are applying an overload to induce somehow residual stresses, and then we go with fatigue. And we consider it as the reference curve, let's say. Then we apply, and this curve is represented in terms of residual stress by this curve. So preset, this is the SN curve with a fatigue limit around 140 KSI, and this is the corresponding residual stress curve. And what can we note is that we start from compressive layer, but the depth of the compressive layer is quite limited. And after 5 minus 3 inches, it goes to 0 and then becomes tensile or anyway negligible. Then we have the other curve, the second curve that we examine is the conventional shot peening. We are using shot peening. We don't care now in this slide about the parameter. We assume that is well done. And with conventional shot peening, we are able to improve what we can get by using preset only. That is to say, we are able to increase the fatigue limit from 130, 40, let's say, to 150. Okay, and this can be associated to a different residual stress then, that is this one. In this case, we can recognize the typical trend due to the residual stresses, that's due to shot peening, sorry, with a compressive value and then a peak under the surface, and then at 10,000 inches, it gets 0 and then becomes tensile. So we notice the effect of residual stresses induced by shot peening. And then what can we see? That if we are applying shot peening with preset, we are applying what I call in the first part of the lecture this morning, stress peening, that is shot peening while we are at the same time contemporary applying a mechanical load. If we are doing that, this is spring, right? If you are doing that by considering the right side of the spring, that is with the same sign plus, we are increasing the final compressive residual stresses. So if you are applying stress peening with shot peening plus pre-stress with 0.3% pre-stress load, we are able to increase the limit, and this is due to what? This is due to the increased compressive residual stresses. Okay, this is clear. And so we are able, by increasing the residual stresses due to this modified shot peening treatment, we are able to go from 150 KSI in terms of fatigue limit to 180, more or less. And if we are increasing the load of preset of stress peening on the right side of the spring, of the leaf spring, let's say, so plus we are doubling the load for stress peening, we are improving again the limit to 200 megapascal. And this is related to a further improvement of the compressive residual stresses here, the solid line. At the same time, if you are applying the same pre-stress on the wrong side of the leaf spring, okay, we are inducing a negative modification of the stress residual stress induced by stress peening. They are almost negative, almost null, like this case, 0.3, minus 0.3, and even positive, minus 0.6. And we notice that in this case we are decreasing the final fatigue limit. This is to underline the importance of the initial residual stress state in determining the final fatigue limit of the part. Okay. Is it clear? So there is a direct relation, not linear, but there is a direct relation between residual stresses and fatigue limit. This is clear. And if the residual stresses, compressive stresses are increased, this will correspond, not infinitely, but anyway, will remarkably correspond to an improved fatigue limit of the treated material. Okay, and this for residual stresses is okay. So, about surface work hardening, this is the second effect. The impact of multiple shot causes surface work hardening and the grain distortion. If we are considering even severe parameter, we can also induce grain refinement and recrystallization. Okay, and this can be obtained by using more severe Almen intensity values or coverage values. It's true that if you are increasing the Almen intensity to induce grain refinement, indeed, we can also induce overpinning or surface damage. So if you want to go with grain refinement, it's better to think to increase the coverage, even if this makes the treatment more time-consuming and so less cheap or more expensive. And then do not forget that in this severe shot peening, grain refining is okay, but if we are exaggerating, we are going to get overpeening, and this is a not wanted condition, because in this case we are going to decrease the effectiveness of shot peening. Okay. This is a qualitative graph that gives an idea of the role played by residual stresses and surface work hardening induced by shot peening. Okay, this is, I assume is, and I want you assume is as qualitative, because the quantitative scale varies with the material. Okay, we have fatigue life increasing in the vertical axis, but the hardness in the abscissa, and we see that indeed the role of residual stresses is getting more and more important for harder material. Why? Because for this material they are not less prone to relax after the application of fatigue cycle. Anyway, both these effects should be considered. Or in other words, if you are pinning material not very hard or not with not high strain material, let's say, it's good to consider that the main effect could be not residual stresses, but also surface work hardening. Okay, because the residual stresses for very soft material tend to relax after with the fatigue cycle applications. Okay, and indeed, and here there are some result that and I would like now to comment. Maybe we will do that tomorrow now, and about what we did about surface work hardening. This is we developed research about the application of unusual parameter of shot peening, that is we call CV shot peening, as I said, and we want the aim was to investigate how shot peening, which is the role of shot peening in obtaining gradient microstructure and grain refinement, and which is the final effect on the fatigue strength of the material and of the mechanical part. Okay. Okay. If there is any question, I think you are also tired now after all the morning spent listening to me. If you have question, I'm here.
Professor, slide number 15. What is that point? How do I read that 0.60 percentage? How do we read that? What is that point? How do we read that 0.60 percentage means?
Okay.
In terms of strain?
This means that we are using, imagine you have a leaf spring, okay, and you are changing the stress, and you are using stress peening. That is to say, you are using a load that is stressing, that is bending the leaf spring, and at the same time you are using shot peening to pin one side of the spring. 0.3 and 0.60% means the percentage of the extra load you are doing with respect of shot peening. Okay, this is what we are doing. Okay, this is a limited load, okay, but not enough to cause plastic deformation, but is increasing the final residual size. The difference between minus and plus is that we are pinning two different phases of the leaf spring. And since the load in leaf spring is just in one direction, if you are pinning the wrong phase, it means that compression will go on the part that is not critical during the service operation, during fatigue. And so we are decreasing the final fatigue limit.
Percentage refers to load there.
Sorry?
Percentage refers to increasing the load.
The load, exactly. I don't know the number of Newton, but anyway, this is increase of the load, yes.